Okay, so today, this is take 3 on our intro. That's why it's so kind of funny. But anyway, so today we have homework due, and some people said that there were some questions about the homework problems. So, questions?
Not late. I got a question.
You have a question?
Yeah.
On which one?
On kind of just in general. This is
A general question.
when you know how you cannot use textual substitution for the steps, right?
You use, when you go from one to the other, you substitute equals for equals.
Yeah.
Or, and actually now we have a new one. You can either substitute equals for equals, or if this one implies this one, you can put it implies there.
No, I mean, using the assuming the conjuncts. When you're using that.
Oh, with assuming the conjuncts, you start.
Use textual substitution in the.
You cannot use textual substitution in the conjuncts, in each individual conjunct. You can,
just in the conjuncts?
yeah, right.
Oh, okay.
You cannot use textual substitution in the conjuncts. The conjuncts are not theorems, but they are constants that you assume are true.
Got it.
So when we're doing our proof in the hints, we write assumption of.
You write assumption, and then you give what the which conjunct you're assuming, and
that would be true.
and you can have that be true. So and because it's true, you can use it just the way you would any other previously proved theorem. I mean, like if you were to write that down, you can think, oh, that's a theorem. I can use this just the same way as if it were a theorem.
Can you write like that, like assume P and Q and then just use it?
Yeah, write a proof when you write proof assume conjuncts of antecedent, or assume conjuncts, and then I'll know, and then the reader will know that whenever you do assumption, boom, what you're talking about. You're talking about the. And at the beginning, yeah, you always have to say what kind of proof you're using.
No, in the hint, do I have to write assumption?
Yeah, right. Assumption, yes.
Can I write P implies Q if I already said assume P and Q at the very top?
Well, okay.
Thank you.
But I prefer you write assumption and then, anyway. Because you're using the technique of assuming the conjuncts of the antecedent. Okay, good deal. Any more specific questions? Do you want to, let's see, what did you have due today? 4.1. Oh, reprove 4.1 using assume the conjuncts? Okay.
Could you just do an example?
Prove 4.1.
It doesn't have to
Yeah, it was prove 4.1 and reprove 37.
Oh, let me see. Assume the conjuncts of the antecedent, huh? That's with an implies. Here, let's. I thought we did one last time. What are we trying to prove? 3.76e, or is that what?
377 reprove it.
Oh, reprove 377.
And then prove 4.1.
Okay. Well, why don't we prove 3.76c by assuming the conjuncts of the antecedent?
All right.
Okay. This is a reproof. It's not a true proof. It's not a true proof, it's a reproof, right? Okay. And we will assume conjuncts of antecedent. And so what is a 3.76e? That's
P and Q.
or C. Did I say? I said E. I meant C. Sorry. Yeah. 3.76C. And that's P and Q implies what? P or Q. Okay. So now, whenever you assume the conjuncts of the antecedent, you always start with the antecedent. And you have to get it to equal true. You don't get it to imply. You have to get it to equal true. Sorry. You start with the consequent. Boy, I'm getting everything, everything.
You need a vacation.
Yeah, I need a vacation. You always start with the consequent. You always start with the consequent. Okay, so and you have to get it to equal true. You can't get it to imply true. You got to get it to equal true. Are you with me? Okay, so we start with P or Q. So this equals Now, one of these conjuncts is P, right? So here we have assumption or assume P, so that if we assume P, that's true or Q. Yeah? Now what?
0 of all.
You assume
You wouldn't need to consider that true or something, so it's always true.
Right. So this is 0 of, or, you have a number for me here?
Yeah,
No.
3.29.
3.29. So true or Q is what? True. Boom, we're done.
You have to say which is.
No, true is good. Is everybody, are you with me on this, how that works?
You always write which is if it's not just true.
Well, yeah, if you get it to a previous one, then yeah. You can, if you get it to a previous one, then you can say which is, yeah. But true, we all know. Is everybody clear? Did this answer your question about how to do assume conjuncts of the antecedent?
Could you assume Q as well? So it's
You could. You could either, you could, actually you could assume Q and you would get the same thing, or you could actually assume them both and you'd get true or true. And get,
so either way is right.
Either
On
way
the
is-
homework?
either way is fine.
Okay, because on the homework I assumed we both.
That's fine. That's fine.
So anytime you assume the conjuncts, it has to equal true?
You have to start with the consequent and get it to equal true. Because what this is saying is that if this, you know, if you use this as if it was a theorem in the proof, then what you're saying is that the truth of this depends on this. See? So.
And we can only ever use that technique if the antecedent has conjuncts.
Well, the number of conjuncts is, it works with any number of conjuncts. And it could be, you could have 2 or 3 or 4, but you could also have 1. In which case there really isn't a conjunct, but it works anyway. Are you with me on this?
So even if like the
So we could,
antecedent is
You can prove P implies Q.
P implies R, that's, P implies R implies Q. Could we say P implies R is a conjunct of the antecedent?
okay, if you had, say that again, if you had what?
P implies R
If you had P implies,
implies Q.
well now,
P implies
you,
R implies Q.
okay, but you have to put the parentheses somewhere.
The parentheses would be around the P implies R.
Around this.
Yeah, so could
Then you would start with the Q, and this would be one,
we can assume that as
this
one.
as one conjunct, yeah. But you would start with Q and you'd get it to true. Good questions. Any more questions about the homework? I handed back the homework, so, from last time. Any more? Is that all you, is that, you did, was this mostly just assuming the conjuncts of the antecedent?
I have a question where my homework is.
Oh, your question is where's your homework? Does somebody have? Okay. All right. Well, if there are no more questions, then we are going to go to the next proof technique, which is okay, so we've done assume the conjuncts of the antecedent. We did case analysis. Yeah, so the next one is proof by mutual implication. Well, there's not a whole lot to say about this because the only reason that we include it here is actually there is, I can think of maybe one proof next semester where we will need to use proof by mutual implication. So let me just make a comment about how generally not useful this is. Okay, so proof by mutual implication. Okay, and it's based on 380. Let's take a look at 3.80. So here it says 4.7 mutual implication to prove P equivalents Q, prove P implies Q and Q implies P. So let's take a look at 380.
That's what it is.
Yeah, 380 is mutual implication, and notice what it says. It says P implies Q and Q implies P equivalents Q. Are you with me? So one way, if you have a theorem that has the form P equivalents Q, you have some expression equivalents another expression. One way to prove it would be to assume the left-hand side and get it to imply the right-hand side, and then in the next step, again, this is like two subproofs, kind of like case analysis. And then in the next step, start with the other side and get it to to that side. So you prove it in both directions. So it's clearly based on 380. Now, so it's based on 380, which is, P implies Q and Q implies P equivalents Q. This parentheses is really unnecessary because we have a equivalence here, but we just put it there for emphasis, okay? And let me just make a statement about this. It's common in mathematics, not so common in formal methods. In fact, it's so not useful that I struggle to find I'm not even going to give an example, and I'm not going to give you an assignment.
We use it for sets, right?
Well, there's this one. I don't think we use it when we get to sets, but I think we use it. There's functions when we do functions and relations, and we do. I think there's one where we use. There's a theorem. There's a theorem where you start with one side and you get it to the other, and you start the other side and get it to the first. It's a more advanced topic that we'll get to next semester. So, that's all we're saying about it. Actually, there's one more thing actually though that I do want to say, that I do want to point out, because 3.80, notice that 3.80 says is mutual implication. P implies Q and Q implies P equivalents Q. But what I want to point out is this is similar to 3.82.1. This one's not in the book, but I think this is a good one to note. It's P equivalents Q and Q equivalents R implies P equivalents R. So this is another one where you have a P equivalents R here, but we have an implication here. And this is so, I would like to actually prove 3.82.1 and point out how it's different from 3.80. Because it's kind of interesting. I think it's good for us to compare and contrast these two. So let's take a look. Let's prove 3.82.1, which is P equivalents Q and Q equivalents P implies, it's QR. Yeah, actually this is a little different because it's got three of them, right? Implies P equivalents R. So what we're going to do is let's start with the left-hand side and get it to imply the right-hand side. Now we're going to use, one reason I want to do this is we're going to use a theorem that comes, this next theorem is, or the theorem that we use here is one that comes in really handy sometimes, and it's one that we haven't really emphasized yet. So let's start with the left-hand side. P equals Q and Q equals R. And the theorem that we're going to use is one that we haven't talked about before, 3.51 replacement. Now I want to see if somebody take a look at 3.51. We haven't used this before. I don't recall. Do you ever recall using 3.51 yet in a proof? This is interesting because what it says is that if you have P equals Q and R equals P, so if you have two equalities, of which one is, how does that work? Of which one of them is the
Two
same.
things are equal, then they're both equal to something that the other one's equal.
Yeah, does that make sense?
Isn't that kind of like Leibniz?
It is kind of like, yes, it's kind of like Leibniz. You're right. It is kind of like Leibniz, but it's in the form of a theorem. Okay, so it says if P equals Q and R equals P, that's the same as P equals Q, and since R equals P, then it's the same thing as P equals Q and R equals Q, because after all, P equals Q, right? But they equivalent. It's kind of interesting that they equivalent like this. Okay, so how would this be? So what would this, using 3.51 replacement, what would this be? P equals Q and what?
P equals R.
Yeah, very good. So that would be P equals Q and, what'd you say? P equals R. Now what are we trying to get this to do? Well, because what are we trying to prove? What are we trying to get it to do? What are we trying to get it to do?
To imply P equals R.
Yeah, so does it?
Not yet. Or does it?
Have this, oh my goodness. Come on, you guys. How many? Now this one, 3.51, I agree, is one that we haven't used a lot. But now we're talking about one that we use a whole lot.
Really?
You should know this one by now. My goodness. Eh. Come on, you guys. P and Q. P. How does that work? If you have P, no. If you have P, I know you guys are going to kick. Yeah. P or Q. So how does that work? P and Q does what?
It is. It's strengthening the end.
Yeah. P and Q does what? Implies P. That's what? Strengthening or weakening? That's strengthening. How does it work this way?
P or Q
Follows from P.
Yeah. P or. Is it P implies? Yeah.
Implies, yeah.
Yeah, P implies P or, yeah. Yeah, oh, I hope you know this one. So what do we have here?
You have,
We have and.
yeah. P
Oh.
equals Q.
You have ands.
P equals
Because of strengthening the antecedent, we can get rid of the P equals Q.
Exactly. So this implies by strengthening. And which one is that? 3 point what? 3 point. I thought strengthening was A.
No, weakening is a.
Oh.
is strengthening.
And so this implies P equals R, right?
Check that.
Yeah? Oh, these okay, so these are all good things for us to go over and get cemented in our mind.
Implication thing, or is that
Well, I mean, this is a proof that P equals Q and Q equals R implies P equals R, which is a what? This is a, what kind of a law is this? P equals Q and Q equals R implies P equals R. This is what kind of a law is this? It's a transitivity law. Is that what it says?
Yeah.
382.1.
Yeah, it says transitivity of equal valence.
Yeah, transitivity of equal valence. Okay, but now here's what I want to show you. What about this? Why is this implies and not equivalence? So note that P equals Q and Q equals R equivales P equals R. Is this a theorem?
No.
Yeah.
Yes.
No, P equals Q and Q.
No, yeah.
Is it or is it not a theorem?
Nope.
I don't think it is.
If it is, I haven't.
You don't think it is? Can you prove that it's not? Note that this is not a theorem. How can we show that something's not a theorem?
Disprove it.
Well, we can show well, in order for it to be a theorem, what does it have to be? True in what? So it's all you have to do to show that it's not a theorem is show one state where can somebody come up with a state where it's not true? It's not a theorem because so here's your because Q or P, yeah, because P something Q something R something. So can you put in a true false here, a true false here, a true false here that makes this not? So if P is true, come on you guys.
Q is false.
Q is,
False and R is true.
Yeah.
if Q is false, and R is, are you saying this is a counterexample?
You can either have one false or three.
Yeah, so if
Right, the three falses.
P is true and Q is false, so this is false and anything is going to be false, right?
False and false.
False and false make true.
You can have the P false and have the Q.
False and false.
And then, okay, wait, let's carry this through. So if P is true and Q is false, then this is false, right?
Right.
False and anything is false. So we'd have false equivales, but P and R are true, so that'd be false. This is true. So we'd have false equivales true. So that's, yeah. So this is a counterexample because this is a. But there's no way that you can get a counterexample to this one.
Impossible.
Because this is true in all states because we proved it. All right? So anyway, I thought those were, even though this is just tangentially related to proof by mutual implication, I thought that was an interesting compare and contrast. Okay. Now, the next proof technique that we're going to use, we're going to learn, is one that is slightly more useful in formal methods. And this is called proof by contradiction. Now, before we do proof by contradiction, I want to actually prove this theorem 4.9. And what does theorem 4.9 say? It says not P implies false equivales P. So not P implies false equivales P. So here's the proof. Well, here we have an equivales. So what do you think we should do? Start with the left-hand side. Good deal. So let's do not P implies false. Well, suppose I gave you a little pop quiz here and said, prove this. What would you do? Get out your equation sheet. Yeah, obviously. But I see all the equation sheets are out.
374
Yeah, that's like the exact opposite.
with P replaced
Three.
by not P.
Using what? Three what?
Oh, yeah,
374 with
374?
P
Oh, I was gonna use our old friend.
No, this one's better.
No, I like
This is
374.
not
374 is a
Now you-
lot better.
374.
I thought
374 is better because then you have not.
Oh, you have a better proof than the one I did. I was gonna use not our old friend 3.59. It would be not this or this, right? And then not P would be P, and then that would be P or false. Well, anyway.
No,
But you want to use 3.74?
much better.
Okay, we'll go your way. Equal, is this equals? By 3.74?
Yeah.
Equals,
374 with P replaced by not P.
It's just not
Equals
P.
Not P?
And then not
so
P.
it's not P, which equals by
312.
double negation.
Yep.
Yep. Okay.
Oh, you guys are good. You improved my proof. I would have had a not P or false, but it would have been, yeah.
Yeah.
Okay, good deal.
You should send that into a book.
You want to be published in the solutions manual? All right, so so here's proof by contradiction is based on 4.9. Proof by contradiction is based on 4.9. Actually, this one, there's a really important proof in computer science. It's the, maybe our cameraman remembers the halting problem. Do you remember having to solve the halting problem? The halting problem is solved by proof by contradiction. When you need this, this you will run up against a lot in computer science. And so it's proof by contradiction is based on 4.9. And the way it works is to prove P. So here, look. What does this say? Equivalence P. To prove P, it's equivalent to doing what? To prove P, it's equivalent to doing what? To assuming not P and getting that to imply false. That's why it's called proof by contradiction. The thing that you're trying to prove, you assume the opposite of it.
Sure.
And you get it to imply false. So to prove P, the way it works is like this. To prove P, start with not P. Actually, he has a capital there. To prove P, start with not P and get it to imply, but here's the thing.
So the first line of the proof is not whatever.
Yes, but you have to say proof by contradiction, otherwise I'm thinking, where did the not come from? Okay, so start with not P and get it to imply, but now check this out, you guys, parentheses, or equivalent. False.
So it might not, it doesn't have to imply.
Well, but if it equivales, does it imply? If it equivales, does it imply? If P equivales Q, then does P imply Q?
Yeah.
It does. So you're proving more than you need to when you get it to equivalent. Now, is everybody following that logic that I just?
Do the strengthening here, okay? Like P implies Q.
Q and Q implies P.
Implies by strengthening P implies Q.
Mhm.
So when you do equivalence, it's the same thing as.
Is everybody clear on that? So when you do proof by contradiction, if you get it to equivalent, you've gotten it to imply anyway. So you get it. You start with not P and get it to here.
Equivalence that it has mutual implication.
Yeah, that's why I'm displaying all of this stuff.
False would imply not.
All right, so let me show you. Let's do one where we actually negate it and then get it to equivalent false. Okay, so what we're going to do is let's reprove. So here's an example. Reprove 3.15 using proof by contradiction. Using proof by contradiction. So let's take a look at 3.15. So 3.15 says not P equivals false. Now,
Proof by contradiction.
we're going to use proof by contradiction on 3.15. Okay, so now remember, we can only use what went before. Well, okay, so what do we start with? We start with not parentheses, yeah, not parentheses, not P equivals false. Not P equivals false. So now do you see how we start? What we do is the thing that we're trying to prove, we say, oh, we're going to use proof by contradiction. So we assume it's not the case that blah, blah, blah. But now, you're right, now we can't get it to true, we got to get it to false. All right, but what's really neat about this one is now that we have this not P equivals P, how does not distribute over equivals?
To whichever one we want it to.
To whichever one we want, but obviously which one do we want it? The first one. Okay, and which theorem is that? That it goes 3.9, yeah? So equals by 3.9, so this not will go in front of here and we'll have not P equivals false. Are we good? And now obviously what do we have?
Double negation.
Double negation. And that makes what? P equivals false. And now this equals by 3.3. You said 3.3, right? And what? Well,
True equivals false.
yeah, this would be true. Yeah, P equivals P is true, right, by 3.3. So this is true equivals false, which, well, but by what?
By 3.3 again.
By 3.3 with
Replaced by false.
Yeah.
Could you say
3.3
Yeah.
with, yeah, you could. Q replaced by false, so this is false. And boom, we got it because it's by contradiction, so we get it to false. Notice in this case we didn't need an implies. In this case we just got equals the whole way.
We couldn't use an implies on this one because there's no implication before 3.15. There are no theorems.
Oh, you're right. There's no theorems of implication. That's funny. Yeah, well, like I say, these are reproofs. Yeah.
But if we're doing a reproof, can we use theorems that come after that?
No. We're assuming we're using this technique, but we're still.
The technique is not dependent on the other theorems.
Well, remember we started this whole section, this whole chapter with the fact that these proofs are not really proofs, they're just good exercises. But to keep them to be good exercises, let's just use the proof technique, but we will assume that anything that we use has to come before, okay? Otherwise, they would be, well, that would even be a worse of a reproof. I mean, if you could use stuff after, I mean,
I have a quick question.
yeah.
Say we go back to the step where we have P equivals false.
Yeah?
Can't we just say that P equivals P is true because of 3.5? No, we use 3.3.
Well, oh, you mean what's 3.5 as opposed to 3.
That's the same thing.
Yeah. Yeah.
Well, could you have done that for the not P equals P? And just
Yeah, because of double negation.
So you know that it's true, right?
Oh, yeah.
What?
If you go up to double negation,
No,
not P equals P,
equals
is double
true.
negation, is the theorem.
It's
Yeah.
true.
Oh, this is a theorem, not P equals P. Yeah, we could have used the theorem and we could have made that true right off the bat.
Yeah.
Oh, that's interesting. We used double negation to get it to here, but we could have used double negation to get it to be true equals false. Oh, that's good. That's quite nice. Okay. All right. One more proof technique, and this one is kind of handy. And this one is called, drum roll, proof by contrapositive. Now, it's kind of interesting why this is called proof by contrapositive, because it's based on, now do you remember what the contrapositive, it is an implication equivalent to its converse? Do you remember what the converse and the contrapositive are?
No.
You don't remember? Okay, a little review time here. Okay. So the converse of P implies Q is Q implies P. The contrapositive of P implies Q is, do you remember what that is?
Not Q
Implies not P.
Not Q implies not P. Okay, so now here's my question. Is the converse of P implies Q equivalent to P implies Q?
Yep.
Are these two equivalent?
No.
So the answer is no. Is the contrapositive of P implies Q equivalent to P implies Q?
Yes.
Yes, these are equivalent. Are you with me? Does everybody remember this definition of converse and contrapositive? Huh? Well, this was on the board, and we did
it at one point.
We did it at one point. I think when we looked at the contrapositive theorem, I think maybe it was when we were doing truth tables. Yeah. It's one day when nobody was here. It's one day when I was lecturing to an empty house. Okay.
It's pretty easy the next time, too.
Okay, so which one is that? The contrapositive? Which one is that? Which one was the?
That was the converse.
Here it is, 3.61. So 3.61 says the contrapositive, P implies Q equivales, not Q implies not P. Well, this is called proof by contrapositive. And look what it says. Look at what the proof by contrapositive says. It says, to prove P implies Q, prove not Q implies not P. Well, I mean, the only thing that makes this different is that, I mean, if you're going to start with the whole thing, the first step could be contrapositive, and then you could just go on from there.
Yeah.
See what I mean? On the other hand, if you want to prove that P implies Q, you can say prove not Q implies not P. Then you might start with, for example, not Q and try to get it to not P, or you could start with not P and get it to follow from not Q. See, but
Or you can start with Q and get it to follow from P, or P to imply Q.
or you could get it to, well, yeah, but if you're going to start with Q and get it to follow from P, then you're not using proof by contrapositive. Okay? All right, so let's do an example. Let's do an example. This is an easy one. Let's reprove 3.76b. Reprove 3.76b, which is P and, oh, our old friend we just looked at. P and Q implies P. Okay? So what do we start with?
Not P implies,
So we start with not P implies what?
not P and Q.
Not P and Q.
Wait. Can't we start with one side now?
Well, I think,
Assume.
well, you want to start with one side?
We could.
Okay. So we must prove this. What we're saying, do you want to start with just one side? It's fine with me. Okay. Let's reprove 3.76b. I was going to do the whole thing, but
Let's just do
How
the
do
whole thing.
we not distribute over?
It says.
so we're going to reprove. We're going to reprove this. So so here's what we must prove this. Okay. So which side do you want to start with? I think we should start with the right-hand side because it's got more stuff, right?
Probably.
Yeah, we can do that. Yeah, and then you use.
Okay, so let's do not P and Q equals by, well, what's an obvious thing to do here? De Morgan, which number is that? Is that before 376b?
Yeah, it's 347.
So De Morgan, that would be what?
Not P or not Q.
Not P or not,
Then we use weakening.
yeah. Now is that which does what?
Follows from not P.
Follows from weakening. Which one is that?
76A.
Is that, oh, we used the one right before that.
Follows from not P.
Follows from not P, and we're done, right?
Yep.
Because we needed to get this to follow from this. Oh, that was, actually, yeah, that's better than the way I was going to do it.
Yet again.
Yeah.
For 3, man.
3 strikes, you're out. See ya.
All right. So that completes the proof techniques in chapter 4. We have about 3 minutes.
Party!
You want to? I hesitate to ask you this, but do you want to get out early? I have another slide. I mean, we could start chapter.
So were you?
We could start chapter 5, but
Have I ever been talking about food?
yeah,
No, I already absorbed so much.
you already absorbed so much. Was that with the absorption law?
Yes, with the absorption.
Okay. See you tomorrow.